This is the ELTE260 Module B or Week 2 video lecture. So what you're going to do is you're going to click on the link to watch the lecture video, which is this right here, and you're going to pause the video when I tell you to, because there's some other links that you want to do. And then you're going to look back at the PowerPoint, and then you're going to fill out the lecture video worksheet. And then you're going to complete the component identification activities, and then you'll turn the completed lecture video worksheet. So here's our outcomes. We're going to learn about the basics of a PLC: CPU, power supply, I/O, programming, terminal, and rack. We're going to talk about how do different solid-state switching mechanisms used in the I/O modules work, such as transistors or thyristors. What are the differences between sourcing and syncing input modules? How do you access the I/O data table? What is an I/O address? How can the data table be used to address program instructions? And what does mapping the I/O consist of? What are the parts of a PLC Program Scan? And what are the steps to program, download, run ladder logic programs using RSLogix? So by the time you get done with this video lecture in the lab, you should be able to answer all these questions. A PLC is a programmable logic controller. It's kind of like a computer, whether it's a laptop, desktop, or your personal device. It's just for industrial applications. It has three main purposes: to replace relays used for logic, it replaced time relays, and then it incorporate count control. Those were kind of the main things when it first came out. And nowadays, PLCs are much more complicated and do a lot of really more complicated things. But that was kind of the basics when the PLC was implemented. So, for example, in 131, you've had pneumatic timers. Well, a pneumatic timer, the purpose of that is to delay the operation of a control component. You wouldn't just hook up a pneumatic timer to perform something. It has a logic purpose. And those were replaced with solid-state timers that you'll use in class. And those are just, instead of pneumatic bellows, they are electronic. Latching relays, once again, a latching relay or a control relay, you wouldn't hook one up. You just use it for logic. And solid-state counters, you wouldn't turn on a counter. A counter is just part of logic. So those are some of the control components that are easily programmed into a PLC. Let's take a look at this for example. So if we take this logic here, when I push this 1 PB, the TR is energized and the instantaneous contacts on the TR close. So I've created memory, okay? And then the instantaneous contacts here close and I get a red light. So hit the button, I get memory, and I turn on a red light. And then I have a timed, and it's going to time close, and then the green light would come on. So what devices are we turning on? So in this case, we'll turn on a timed relay, red light, and a green light. But really, in your circuit, the things that you probably really care about are this red light and this green light. But we had to wire up this timed relay, we had to wire up this holding contact, and we had to wire up all these contacts here, just in order to really, all we want to do was have this push button turn on these lights. Okay, so what a PLC does is it takes this timer, here's my on delay timer, and we don't have to wire it up. It's just part of a computer program. And this contact right here, we don't have to wire that up. It's part of the computer program. These contacts here are internal fictional bits associated with this timer. So all we have to do is wire up this push button and these two lights, and that's all the real devices that turn on. This other stuff here just exists in the computer. Okay, PLC advantages: smaller physical size than hardwired solutions. When you start doing hardwired solutions, they have all these big timers and counters and control relays and everything like that. We get rid of all that. It just goes into the computer. It's just a computer operation, and it's fictional. It's easier, faster to make changes. We'll take a look at that. If you want to change a hardwired control system, you got to get out your wire cutters and your screwdrivers. On a PLC, you just change the program and maybe add some more I/O. It's very simple. PLCs have integrated diagnostics. They tell you what's going on, help you troubleshooting. You can easily document your programs to help troubleshoot. And if for some reason you build a machine system and you wanted to, mass produce it or make more of them, it's very, very simple to do. You don't have to rewire all these massive systems. You just wire one system and then copy the program over. So what you're going to do now is we're going to take a look at Jeopardy game, hardwired versus programmed. This is on your lecture worksheet, so you want to use a pencil as you're filling it out. The first one you want to do is you want to stop and you want to watch this video, and then secondly you want to stop and you want to watch this video. So go ahead and watch those videos and fill out your lecture worksheet. So hopefully that made sense. Those hardwired Jeopardies and programmed Jeopardies. Let's talk about hardwired operation again. So when you do hardwired operation, you're going to have actual symbols. So if you had an input here, if it was a toggle switch or a limit switch or a float switch or something like that, that is going to be what you see for the symbol. And that's from your 131. And your output here would be a light or a solenoid or whatever you're turning on. And so that's where you're going to see your ANSI or NEMA symbols. In the PLC, though, the PLC programming doesn't use all those symbols that you spent so much time learning in 131. Those symbols are still used when you do the hardwired diagram for the inputs and the outputs that get wired into the controller, but the PLC ladder logic programming utilizes only contacts and coils. So our inputs, everything is going to come down to an examine if closed, which looks like it's an open contact, or an examined if open, which is going to be a closed contact. So those will be on the inputs, and your outputs, for example, are going to be your output energized, which is just going to be the symbol for a coil. So PLC programming, examine if closed. Well, this contact could be associated with a limit switch, but the PLC, when you program it, you just put in a contact. You can't program in a limit switch. We associate this with a limit switch, but there's no symbols. So PLC Operation and Scan. So here is into the input module. There's your symbols that we've learned out of 131. That's where you would draw the symbol of the limit switch or toggle switch or whatever. It gets wired into an input module, and the input module does some conversion to tell the CPU whether it's been opened or closed. The CPU looks at my ladder. It looks like the ladder here is a toggle switch, and once again, it's not. It's put in as a contact. It's not put in as a toggle switch, and the lamp is put in as a coil. It's not put in as a light. Okay, so if this closes, the lamp comes on. So input, there's my CPU logic, and if it becomes true, my output module becomes true, and it delivers voltage to the lamp. So that's the PLC Operation and Scan. So basically, a PLC, a SLC 500 second generation would start by scanning all your inputs, all your switches open or closed. And then what it would do is it would take a look at your program, your ladder logic program. So based on your ladder logic, it would start closing or opening all the contacts or putting ones and zeros in there. We'll learn about the data table. So inputs, and then it takes the program and it forces the inputs into the program, and then it updates the outputs and writes those. So then the outputs then turn on or off, and the outputs could be connected to lights and solenoids and everything like that, or these outputs could be connected to internal bits, and we'll do that. And then it keeps going: inputs, ladder logic, outputs, input, ladder logic, outputs. There's a little bit of housekeeping that goes on here just to be sure that the scan cycle continues to run. Okay. Truth table examples. So what you're going to do is take a break here in your lecture worksheet, and you're going to watch some truth table videos about your and/ors. Okay, taking a look. Hopefully that made sense. And now what we're going to do is we're going to delve into our ladder logic a little bit using XIO and XIC. your open and your closed contacts, and then how we associate internal bits or internal contacts with OTE's fictional outputs. Okay, so take a look at these ladder logic, this one, and then this one, the second one, and then the fourth one. Take a look at those and fill out the lecture worksheet. All right, that logic's looking pretty cool. All right, let's talk about PLC components. We have inputs, outputs, CPU, power supply. It's very similar to a PC. Like I said, you have a smartphone. You have an input where you have a touch screen and you type in search strings or whatever you're looking up. It has outputs. For example, you can plug it into headphones, let's say. And it's got a monitor on it. You have a CPU. You want a bigger and better smartphone. You got to keep buying a new one. It's got a faster CPU with more memory. And then a PLC has a power supply, and with that, we'll talk about that, is that takes power and it supplies the processor. It does not power up the inputs and outputs, but it provides all the internal power. So very similar to a PC or a tablet or a smartphone, something like that. There's different types of PLC types. There's fixed, and this has a set number and type of I/O. And this might include programmable relay. So a programmable relay might have 4 inputs and 4 outputs. A programmable relay might do some basic timing and counting, something real simple. And so instead of, if you had 4 switches and 4 output devices that you're controlling and you wanted some timers and counters, you could use a very inexpensive fixed PLC or programmable relay, and you could get some pretty sophisticated logic with very little wiring, just a little bit of programming. Modular, on the other hand, can be configured to match the needs of the process. What this means is there's slots, and so you can put in, if you need a lot of inputs, you put in a lot of input modules. If you need a lot of outputs, you put in a lot of output modules. Analog, digital, AC, DC, whatever you want. So modular is a little bit more expensive, but a little more versatile. So here's fixed, and so this is an example of a programmable relay. It looks like you plugged in USB here, so it just plugs in your computer. You program it, and on the terminals here, you could wire in certain inputs, and then probably on this side is the outputs that you would turn on lights. And this can do all your timing and counting, and really you don't have to do very complicated wiring, because there's no control relays, there's no pneumatic timers, there's no counters. That's just all fictional. That's just all programmed, and it's just part of the CPU. So there's an example of a fixed I/O. Here's a modular I/O. So what you have is you're going to have a power supply on the left. On the SUC 500, the CPU goes next. On some of the newer ones, the CPU can go in any one of these slots, but initially we're looking at the CPU right next to the power supply. And then you can put in a variety of different items here. So it's going to have digital inputs, digital outputs, analog inputs, analog outputs, some type of transducers, motion control, whatever you wanted to put into these slots. And this one is 1, 2, 3, 4, 5, 6, 7. It's showing a 7-slot rack, but you could have a 13 slot or a 4 slot or a 20 slot, just depending on how complicated your system was, and you would build this rack up to match your system. So go ahead and take a look at, click on this and watch that SUC 500 rack video, and fill out your video worksheet as you go. Okay, so we're going to take a look at this modular rack, either from that last video, or you can take a look at the SUC 500 rack. Unplug the rack, please. Be sure all the power's dead, because you cannot hot swap these items without destroying them on a SUC 500. So on the SUC 500, there's a little button here on the top and one on the bottom that if you reach your fingers in, they just compress, and then this will slide out of the rack, okay? And so what this is a 503 CPU. So for the SUC 500s, there's 501s, 502s, 503s, 504s, and 505s. 501s and 502s are kind of obsolete. 503 is getting close, but there's still quite a bit of this 504 and 505 stuff out there, okay? And so when you open it up, you'll see that there's always going to be a label here that tells you that this is a 17. It'll tell you right here, L524, okay? So that tells you the number of what it is. So if you need to order something, that's where it is. If you have to pull out an input module, output module, this tag right here will tell you what revision and what number and give you all the information about exactly what it is. Let's take a look at our I/O. So the purpose of the I/O is isolation. It keeps real-world voltages away from the PLC. So if for some reason you hooked up something to the PLC input module and you got a huge voltage spike, what you would likely do is you would blow out the input channel. Okay, it would have optical isolation, and that would fry out. The CPU and the rest of the rack would not burn up because there's no physical relationship. It's just an optical switch on that channel of that input module. Termination. It's a place to connect the wires. So you might have a 16-bit input module, as you saw a minute ago, and there's 16 screws, and you can wire in 16 devices. Conversion. They convert real-world signals to that of a PLC and computer. CPUs works on ones and zeros and all that binary math, computer language. That's what they do. They convert it so the CPU knows what it's doing. And indication. There's always good. There's lights on the input and output cards to figure out if it's on or off. So it's great. First part of troubleshooting is to take a look at that light and see if the input's on or the output's on and if it's working. So we have discrete I/O, and that's what we're going to be working on primarily on this class. This first one is digital or discrete, and that's talking about on or off, high or low, 0 or 1. So you'll hear all these terms. So an input, if it's a 0 state, it would be off. If it's a on, or if this gets a 1 written into it, it's on. Same with the output. 0 is off, 1 is on. This is low, this is high. So that's some of the terminology for discrete or digital, just on or off. And devices would be like a limit switch or a light. Discrete input, as I said, is on with ones or zeros, or off with ones or zeros. And here's some typical symbols. And as I said, here's where you're going to see the symbols. These symbols are showing that it's being wired into the PLC input module. Once you take a look at the ladder logic will only be contacts and coils, XICs, XIOs, and OTEs. But your normally open and normally closed push buttons and maintained and limit switches and everything like that, that's where you're going to see your symbols on your discrete input modules. Once again, some more popular ones: limit switch, level switch, temperature switch, push button. You won't see these are digital. You won't see these in the ladder logic, but you would see these on the wiring schematic as they get wired into the PLC. Okay. If we take a look at our discrete input card, once again, you can kill the power. You're not going to be able to pull this out because it's going to be wired in to the system, but what you can do is you can open the door there, as I showed you on that video, and it would tell you what the module is. Okay, and if you weren't sure, you could see here it was a 1746 IA16. That's how if you can pull it out with all these wires and look on the white tag, it would tell you that that's what the input module is. It is a 16-point input module. Discrete outputs, it's either on or off. And once again, discrete or digital is the terminology. You're talking about a motor, it's on or off, or a motor starter's on or off. A solenoid, a lamp, a heater's on or off, motor starter. This LED display is a combination of these pins down here. If you turn on certain ones of these on, then you're going to get different numbers to come up here. Okay, so once again, that's what digital is. Analog input modules would have a range of things like a temperature sensor. It could be 73.6 degrees, but we're not there yet. We're just talking about digital or discrete I/O. Here's my discrete output card. Once again, you can open it up and pull it out, and this looks like this is a 1746 OX8, which is going to be a isolated relay card. The ones in our trainers are going to be DC. This is relay, so it could be wired up with AC or DC. We'll learn all about it, but what you're looking here is for what number module this is, and understanding that it's a digital or discrete output card. I/O address. So we're going to get into a lot of addressing, and the addressing looks like this. So what it does is it takes each one of those screw terminals. Let's say we have an input module, and that's my I right here. Okay, and then what I do is I take that input module and I put it into slot 4 of the rack. So now I know I've got an input in slot 4. Okay, and then on the 4th screw terminal down, I run the wire to a push button. So once again, I have a push button wired into screw number 4 on a card that's in slot number 4, and it's an input card. So that is the address that gets. And so when I program and I put that coil, that ladder logic coil, into the program, I give it this address. And so when I push the button, then the I/O module and the CPU understand that this is becoming true. So we're going to learn a lot about I/O addressing. Here it is right here, input 4, 4. It's an input, it's in slot 4, and it's on the 4th bit. So my logic, these are the things that you might not really ever want to wire up. You know, a control relay or a latching relay, timer coils, counters, and the contacts associated with them. The purpose of installing this into a hardwired system is just to provide logic. You don't want to turn a control relay on to do any useful work. You want to turn on a lighter, you want to turn on a motor, you want to turn on a solenoid. These items here just provide logic, and these are what the PLC replaces so that we no longer have to wire these items up. The CPU, let's take a look at that. So the CPU, it's the microprocessor that has the memory and that does the decision making and processes your ladder, the ladder logic, okay? And as we already went over the scan, it takes the inputs and then it looks at the ladder logic you wrote, and then it solves the ladder logic, and then after it solves it, it turns on the outputs. And as it's solving it, it takes a look at all this relay, counting, timing, comparison, all these operations that you've programmed in there, and that's what the CPU does as it solves the logic and turns on the outputs. Wanted to make just a little bit of a note here about how you hook up a PLC. So what we have here is a master control relay. So a master control relay, you understand all this. Here's your transformer, and you're pulling your control voltage off of here, fused with the e-stop, and then here's a master control relay. So the way this master control relay works is when you hit a start button, you get memory. So what you've done is you've turned on the main power to the system, okay? So let's take a look at it. Let's say this is an AC line 1 right here. The master control relay contact is open, but once we close that contact, then we bring voltage to the sensors and we bring voltage to the output module. So unless you hit the start button, this is not going to close, and it's not going to be held closed, and therefore the inputs and the outputs of the PLC will not work. Okay, but what about the PLC itself? Well, look, it's hardwired, so the CPU is always on, which is good, because every time, you would hit stop, well then the CPU would go off, and then you'd have to turn power back on, and then it would have to run and turn on just like you have to do with a computer and run through all the systems and everything. So basically the CPU is always on, we're just kind of turning off the inputs and output modules. And if you look at this, you'll also see that the DC power supply is always on too, okay? But here's a control CRM, so when that relay turns on, that closes for the AC and that closes for the DC. And this is all a hardwired system that brings power to the PLC and dictates. This is not part of the PLC ladder logic or anything like that. So on my lab notes, you're going to turn the lecture worksheet to the lab instructor. You're going to sign the lab, read the lab carefully. You'll go through and learn how the addressing works and run through a bunch of stuff. And I've already showed you at the beginning of this video kind of how the addressing works. That was one of the early videos for the Jeopardy game, but you're going to get a lot of practice at that for yourself. I'm going to set up the I/O, or the instructor is going to set up the I/O for this lab, so you don't need to do any of the I/O. That's next week. But you will need to establish communications utilizing the information you learned in Lab 1. And so good luck.